Hello, friends. I'm Ashish Arbari, founder and CEO of Aximize. To our new listeners, welcome, and to our old ones, welcome back. We're just going to resume our chat with Professor Supratik Chakravarti from IIT Bombay, with whom I was talking previously about lots of fun things. In case you didn't get a chance to catch up on that, feel free to go and tune in to episode 46. So, welcome back, Supratik. Let's resume our chat. One thing that came up in our chat last week, you mentioned something about synthesis problems. And so tell us a little bit about, I'll let you talk about it because it sounded so interesting. I couldn't miss this opportunity to talk to you about it.
Thanks for asking me because this is what I have been very actively doing last few years.
All right. Okay.
It's kind of one of the topmost priority projects I'm working on the last few years, among a few other things. So the problem in synthesis as opposed to logic synthesis, because logic synthesis in the EDA world basically is that you're already given some functions and you're given some libraries and you want to sort of optimize the implementation of that function using elements from the library for area, delay, power, whatever, right? So what we're working on is not exactly that problem. What we're working on is that you're given a specification which relates the inputs and outputs of a system, okay? And I guess a really sort of striking example of this is that I could just say that let us consider bit vectors, and I could say x equals y1 times y2.
Correct.
Let's say x is a 2n-bit vector and y1 and y2 are n-bit vectors. So I could say x equals y1 times y2, and y1 is not equal to the bit vector representing 1, and y2 is not equal to the bit vector representing 1. Okay? Basically, I want to say that x is a product of two numbers, none of which are 1.
Correct.
Okay. Now, writing this out as a specification is not hard, right? I mean, even if I were to write it out at bit level,
Correct.
I just need to, it's some quadratic complexity.
Correct. Yeah.
But now I tell you that, hey, in this, x is my input and y1 and y2 are the outputs. Y1 and y2 are inputs and x is the output. It's easy, just divide and multiply.
Correct.
But now I take the same formula which relates inputs and outputs, and I say that, I want to synthesize y1 and y2 from x such that this relation is satisfied. Now we're talking about a really hard problem, this problem of integer factorization. And if we can do this for, whatever, 128 bits, 512 bits, we have broken RSA. Right?
Correct.
The crypto systems.
Correct.
So, and it is actually open at this point whether there are efficient circuits for factorization. And factorization is in the complexity theoretic literature. It's not known whether there are polynomial sized or polynomial time-based functions to do this. But if you have bought into this argument that I can specify a circuit by writing a specification, and it's easy to write the specification, but it's perhaps very hard to generate that circuit. So now we are saying that, well, I'll give you just a specification, and you have to design the circuit for me automatically. So in this case, I would give you the specification, x is y1 times y2, and neither of y1 and y2 are 1, and your tool should automatically generate a factorization circuit which can take x and generate y1 and y2.
So in general, we can't have a polynomial time solution to these problems.
We can't have a polynomial time solution. In fact, we have done some work on this where we tried to look at it from a very fundamental level, from the complexity theory level, and we have results which show that, unless long-standing complexity theoretic conjectures are falsified, we can't even have polynomial-sized circuits. I mean, even if you're willing to spend exponential time to synthesize the circuit, you can't even get compact circuits. However,
throw in heuristics.
This turns out to be an interesting problem, particularly in what is called controller synthesis. Okay, basically, you have inputs coming from an environment, and you want to generate outputs that feed into a controller, and you just have a specification about how the inputs and outputs should be related, and you have to actually design the controls of the controller looking at the inputs from the environment. And for example, in things like actually, safety in ML, this does come up because your ML system is not always trustworthy.
Mm-hmm.
So you want to look at the outputs from the ML system, and you want to look at the inputs from the environment,
Mm-hmm.
and you want to generate new outputs,
Mm-hmm.
which ensure that things are always safe,
Mm-hmm.
but it doesn't deviate too much from the ML output, ML device output, because that's perhaps been optimized for something.
I almost feel like we are coming full circle if I look at it from an STE angle, because you remember STE could generate you the counter examples to tell you why a certain input output behavior could be, and would generate those guards coming out of it.
Yeah. I guess there are parallels there. So, but this problem actually is turns out to be that there are multiple ways to solve it, multiple paradigms to solve it. And one of the paradigms that we have focused on quite a bit, and it's now been taken up by other groups, and they have gone beyond what we did, is this business of do an intelligent guess of what the circuit could be, and then check and repair. Okay? And this intelligent guess, interestingly, can be done using machine learning.
Yeah, I was just going to say that. Yeah, correct.
But it can also be done grounded completely in formal methods logic.
Correct.
So there are these two different ways of doing the intelligent guesses, but this guess check repair paradigm has been very interesting. So it's kind of like a counterpart to counterexample guided abstraction refinement, except that this is not really abstraction refinement. This is guess and repair. But there's this other approach which we have, we just have a paper where we were able to achieve a complete theoretical characterization of this problem, where we use what is called knowledge compilation.
Mm-hmm.
Okay, so what knowledge compilation says is that you may give me your specification in whatever format, but then can I compile it to another format? For example, representing something as a BDD amounts to knowledge compilation, because once you represent it as a BDD, things become simple. In particular, this synthesis problem that I talked about, once you're able to get the specification represented as a BDD, after that it's linear time. The synthesis problem is linear time. But of course, the real
transformation,
getting it to a BDD
is this challenge.
And so what we have worked on is to understand that, do we really need a BDD? Can we weaken the requirements for BDDs? And we have sort of reached the point where we have an exact characterization of what is the form that is needed in order to do synthesis in polynomial time.
Nice.
So we have this result, which is just got accepted last month, which says that if there is a specification which can be synthesized efficiently, then it can be compiled to an efficient representation in this normal form that we have now, and every specification in this normal form can be synthesized efficiently. So it can only both ways. And so I have been going and talking about this to, knowledge compilation typically has been used in the artificial intelligence world. And of course, in CAD and verification, we use it mostly with respect to BDDs. But in the artificial intelligence world, they have done a lot of work beyond BDDs. I mean, they have weakened the requirement for BDDs to things like decomposable negation normal form, deterministic decomposable negation normal form, and so on and so forth. And so we have been able to sort of place this normal form for synthesis that we've come up with in that entire landscape, which characterizes efficient synthesis. And this is something, and so now the next step for us is to come up with compilers which do this compilation. I mean, we know the worst case complexity is bad,
right,
but so is it for OBDDs.
Right.
But we know OBDDs really changed the way, right?
Yes.
And the interesting thing is this compilation process actually uses SAT solvers. Okay, and so, because SAT solvers are really becoming more powerful by the day. So we are really hopeful that, we have a preliminary compiler. It kind of does okay, but there's a really lot of possibility for optimization over there.
Awesome.
So this is the new project that I have been working on. This is called Boolean functional synthesis. So you start from a specification of what you want to do, and so from a relational specification, you want to come up with a functional implementation completely automatically. And complexity theory wise, we know that this is hard. But in computer science, we work on so many problems that, maybe 2 decades back, if you showed a problem to be NP complete, that would be reason of
not doing it yet.
Yeah, I mean, say, okay, let's leave it now.
Yeah.
But now we know that if something is NP complete, it's time to rejoice because stat solvers can almost certainly solve it. So,
Cool.
that's been one very exciting stuff I did.
This is a great summary, Supratik. Thank you very much. Now let me come to this last question of our chat today. And I always ask this to our guests, and I think you will offer great value because of your diverse experience. A lot of our listeners are young professionals or students. What would be, in your view, 5 reasons, and there don't have to be 5, there could be more than 5 or less if you think. What are the tips they can take from you to pursue a career in engineering and science?
Okay. So, yeah, this is, I guess, a very loaded question, but
I know.
let me try to give the best answer that's possible. So, I mean, the way I look at it is that a career in science and engineering should be about something beyond just earning your money, okay, and putting bread on your table and a shelter above your head. So, so the first advice that I try to give my students is find out what is it that your heart's calling is for. Okay, I mean, if it is actually doing software design for some students, building software, hacking through pieces of software really gives them the kick, and
Joy,
they can really starve to do that, so to say. And then, they should really look at, I mean, there are opportunities in all of these areas. For some others, maybe just sitting and working out on pencil and paper, coming up with some elegant proofs, coming up with, beautiful designs is what gives them a kick. And I think there are opportunities for all of these various things. For some students, maybe theory has more appeal. For others, building systems have more appeal. I always tell just like the boundary between E and CS is artificial, the boundary between systems and theory is artificial.
Correct.
And I think the greatest living example of this is Don Knuth. And I mean, the man builds LaTeX, and he also proves some of the hardest theorems in theory.
Correct.
So, and interestingly, Don Knuth latest volume is about SAT solving, and he has taken great pains to understand the different heuristics that SAT solvers use, and he has gone ahead and done some beautiful analysis, theoretical analysis of those heuristics, and he has himself built a SAT solver.
Wow.
Okay. Sort of trying to understand what's going on in these heuristics. I mean, that's what a true scientist is about. I mean, he just wants to see things, what's going on. So my advice to, the young generation would be that these boundaries are artificial. So think about what is it that gives you the most kick. And there are opportunities for there. And, because these boundaries are artificial, you can really connect it up to a lot of other things. So do something where your heart lies in, so that
passion is basically the key, and
yes.
Basically don't believe in any religion or any boundaries.
I mean, not every day turns out to be good in any professional career.
Certainly not in science. Certainly
right.
not.
And when you sort of hit the bed at the end of the day, at least you should be able to say, hey man, this is what I wanted to do. This is what gave me the kick.
Cool.
So what if I fail?
Yep.
Right.
Yep.
And so I think that would be my first and foremost advice. The second thing that I would like to sort of emphasize on is that, it's really important to get your hands dirty in whatever you're doing, right? I mean, even when you do theory, you have to get your hands dirty, proving things on your own, coming up with alternative proofs, and so on and so forth.
I remember when you and I were working, when I was visiting you from Southampton days, you and I were coding Verilog together. You're writing scripts together.
Yeah. So, I mean, there is so much amount of learning that is missed out if you don't do it hands-on.
Yes, absolutely.
And, I mean, this, I think, unfortunately, a lot of students these days, think that it's okay to get something from this part of Google, and the Google parts of solutions, put them together and some patchwork, something, as long as it works, it's fine. But you really miss out on the fun of learning, and and that's not the way to learn. And I mean, it's okay to Google and whatever, find out how others have done it. It's okay to learn from it, but I think there's a lot of fun building things
Personal
with your own
experience is
hands.
very important.
Yeah,
Personal experience
yeah.
is
I
very
think
important.
getting your hands dirty teaches you so much about science and engineering in particular. I mean, this is not about philosophy where you just think and philosophize. I believe even in philosophy, getting your hands dirty is very important in
Absolutely.
any field.
Absolutely. I think in everything in life, even cooking, right? I mean, you can read books if you don't cook
Absolutely,
anything.
absolutely. And the third thing that I think, I guess this holds true for every discipline, not just science and engineering, is that there are no shortcuts. I mean, you have to slog it out. You have to spend sufficient time if you really want to be an expert in an area. It takes years. I mean, with going to your college, going to your university, taking online courses can help accelerate the process. I mean, handholding is important, but I think if you're expecting that, I just go through one video recording of some course and next morning I'm an expert in that area, that it doesn't work that way.
No. You've got to get your hands dirty. Yeah.
Yeah, one really, I mean, if one is expecting that, 4 years of undergraduate studies or whatever, 6 years of undergraduate postgraduate studies, and after that you are going to be master of everything in computer science or electrical engineering because you have studied one course on each one of them, I think that is an illusion. I mean, you probably have breadth, you'll understand a little bit of everything, but if you really want to sort of claim expertise in something, if you want sort of for yourself to be known about something that you did, it is important to budget time for that. It's, I mean, there are no quick fixes for that. There
You
are
know
no
what?
shortcuts.
You know what I wanted to say. You are one of the people who reviewed my course, and I'm
Mhm.
really happy and proud to say that all of the individuals that I reached out to say, could you please look at the course, actually went through the course material. They actually took on the quizzes. They actually went to the logical conclusion. And what I really appreciated is that all of you individuals are very busy in your own, projects, but actually nobody did a disservice to me to just look at it cursorily and write whatever you wanted to write. And that speaks volumes for all of the people. And it is exactly what you're saying is put your heart and soul into it. Then only you find
Yeah,
out what is it is in the case.
right, right. Right. So, and maybe, yeah, I don't know how many, I probably talked about 3 points. So there is also one final piece of, advice that I want to sort of, give everybody, particularly the students, is that uh, when we do something, I mean, success and failure, how many patents you got as opposed to how many patents your colleague got, or how many papers you published, how many citations your paper covered, paper, sort of picked up. I think these are quantitative metrics that are used because we still haven't figured out a good way to come up with how to really evaluate a person.
Correct.
And I think we cannot avoid it in our professional lives. We do get evaluated by these quantitative metrics. But, I think one has to look beyond these. And I'm not saying we can completely ignore these because these were affect our professional lives.
They're natural artifacts, side effects, right? They shouldn't be
Yes,
your
but
primary goal.
if that becomes the sole end of our professional career or education, then it's actually possible to game these. And once you game these numbers, you are the loser at the end
Correct.
of it.
Correct.
I mean, you have earned nothing at the end of it. You just game these numbers, and so I think these quantitative metrics are important. They're going to stay because I think the world goes by numbers. But I mean, for every serious student of science and engineering, I think one has to understand that there are limitations of these quantitative metrics, and one has to really go and, I mean, to earn the respect of your colleagues, to earn the respect of your community is a much higher achievement than to get
Make
10
numbers.
more patents than
Make
your
numbers,
colleague
right?
or,
Whether it's patents
yeah.
or I would even say whether it is commercial figures. I'm running a business. I will certainly
Yes,
want to make
yes.
money, but not at the cost of compromising values and all of these things that you mentioned. Hey, thank you so much, man. I mean, we've had a lot of guests, but nobody actually took time to describe the last tip in the level of detail that you did and the other ones. And we talked about so much interesting stuff today, right from your early childhood in the getting interested in transistors radios. I don't think most people even know, the millennials, what transistor radios are. And then asynchronous designs, and we talked about your teaching experiences, symbolic simulation, this exciting work that you and the team at Intel did, and the Boolean function synthesis, which I think is a fascinating piece of work. Thank you so much for sharing that. And I very much value your time today, Shripratik, and looking forward to getting you back again and talking about what else happened after these topics.
Sure. I look forward to. Thanks, Ashish, for this opportunity.
Thank you. Hey, friends, I hope you liked today's chat. Do let us know by emailing us at info@aximise.com. And if you're listening to us on YouTube, please hit the subscribe button and let's stay in touch. Thank you very much.